When a scientist sets out to solve a problem, he formulates a theory. He then designs an experiment to prove his theory. His theory has to pass the scientific method before other scientists begin to accept that his theory may be correct. What this means is that many scientists independently perform the same experiment. There has not yet been a theory of time that has passed the scientific method. The theory of time presented here was chosen because it does offer an explanation of what the engine of time is, and it also outlines an experiment to test this theory. Most of our knowledge of time really is only about measuring it. Albert Einstein figured out a very important thing about time. If you are traveling very fast, then time slows down for you. He also figured out that if you are standing in a strong gravitational field, such as on a large planet, then time slows down for you. We can use this knowledge to develop our theory about time. We need to think about what these two things mean. If time slows down when we are moving fast, then we can consider that motion through space slows time. But what about gravity? How does gravity slow down time? Einstein figured out that gravity from a large planet curves space. He proved that this curved space slows time, but his theory never explained how the matter from a planet curves space. So we know that motion through space slows time, and that curved space from gravity slows time, so there must be a connection between the two. One idea is that space flows into a planet, and this makes the space around the planet appear curved. The flowing space into a planet would cause a person to be moving through space, even though they are standing on the surface of the planet. So both speed and gravity cause a slowing of time for the same reason, motion through space. Time began 13.7 billion years ago with a huge explosion called the Big Bang. So what was our universe like before the Big Bang? For the answer to this, we need to understand another idea called a singularity. As strange as it may seem, a star, if it gets very big and old, can collapse down to a very small speck called a singularity. So what does this mean? Well, it means that matter, like all of the granite, iron, water, and other stuff that makes up the Earth, can be shrunk in size by huge forces of gravity down to an infinitely small speck. It is believed that all of the matter of the universe existed as a singularity before the Big Bang. So where did all of the matter of the universe go when it was shrunk down to a singularity? To answer this, we need to talk about a theory called dark energy. It is now believed that empty space has energy, and they call this dark energy. There are three basic components to our universe: matter, energy, and space. Einstein figured out that energy and matter are equal. If the idea that space has energy is correct, then space must also be equal to matter. Using the idea that space and matter are equal, then it makes sense that when a star collapses down to a singularity, the matter did not just disappear, but was transformed into space. If the entire universe just before the Big Bang was a singularity, then all of the matter of the universe must have been in the form of space. When the Big Bang happened, the universe had reached a point where this big bubble of space could no longer support itself. It began collapsing, and with its collapse, space began being transformed back into matter and thrust back out into the universe. But what if this new matter started out small and has been expanding since the beginning of time? The theory presented here is that the matter of the universe is expanding by the conversion of space, and everything is expanding at a very slow rate. Our yardsticks would be expanding at the same rate as our planet and our houses and our bodies, so there is no easy way to measure this expansion. In fact, it's almost impossible. The expansion is moving in only a forward direction and is very slow, just like time. And this theory gives us our engine of time. We call this theory dynamic matter. Now we need to design our experiment to test our theory. We will use galaxies to help us. All galaxies are spinning faster than they should be. If the matter of the galaxies is growing with time, like in our dynamic matter theory, then this would explain why they appear to be spinning faster than they should. If we measure these speeds that they are spinning and compare it to the speeds that they should be spinning, then we can test our theory of time due to dynamic matter, with a laboratory experiment. We mount a gyroscope in a vacuum chamber and spin it very fast. We then measure how fast it slows down. It should slow down at a rate of 5 times 10 to the minus 16 per second. This is a very small number, and the experiment has to be done very carefully and precisely to measure this change. If we are very careful with our experiment and measure a slowdown that matches our prediction from our theory, then we begin the task of proving our theory. What we then need is many scientists duplicating our experiment. If it passes the scientific method, then we have proven a new theory that explains the engine of time. Perhaps you may one day be a scientist and can also do this experiment to help contribute to testing our theory of time.